Right now, the device you're using to watch this video is slowly dying. Not because of a software bug, not because of a virus, but because the material it's built on, silicon, is reaching the absolute limit of what physics allows. Engineers have known this for years, and for years, they've been searching for a replacement. The answer? It's been sitting in jewelry stores the whole time.
Diamond semiconductors. Not diamonds as jewelry, not diamonds as a flex. Diamonds as the future of computing, energy, space travel, and artificial intelligence. This is the material that could replace the foundation of every device on the planet, and almost nobody is talking about it. But before we get there, we need to understand why the material powering every single device right now is running out of time.
Past 60 years, every computer, every satellite has been built on the same material, silicon. And for 60 years, engineers did something remarkable. They kept making it smaller. Smaller transistors meant faster chips meant more powerful computers. This pattern was so reliable that scientists gave it a name, Moore's Law. But here's where it gets interesting. Physics doesn't care about laws named after scientists. At the scale we're working with now, we're talking about transistors smaller than a strand of DNA. Silicon starts to break. Electrons leak through walls they're supposed to be blocked by. Heat builds up faster than it can escape. And no matter how much money you throw at the problem, you cannot engineer your way around the laws of thermodynamics. Silicon isn't failing because we did something wrong. It's failing because we did everything right and hit the wall anyway.
So if silicon is dying, what comes next? The answer sounds insane the first time you hear it. Diamond. Not because it's rare, not because it's expensive, but because of what diamond actually is at the atomic level. Diamond is pure carbon, the same element that makes up coal, graphite, and every living thing on this planet. The difference is structure. In diamond, carbon atoms are locked together in a perfect lattice, one of the strongest and most thermally conductive structures that exists in nature. But here's where it gets interesting. That same structure that makes diamond the hardest natural material on Earth also makes it an almost perfect semiconductor. It can handle voltages that would instantly destroy silicon. It can operate at temperatures that would melt conventional chips. And it conducts heat 5 times better than copper. Engineers have known this for decades. The problem was never whether diamond could work. The problem was making it.
Let's talk numbers, because this is where diamond stops being a cool idea and starts being a serious threat to everything silicon ever was. Silicon breaks down at around 150 degrees Celsius. Diamond, still functioning at over 500 degrees. That's not an improvement. That's a different category entirely. Breakdown voltage, the point where a semiconductor fails under electrical pressure, silicon maxes out at around 1,000 volts. Diamond has been tested at over 10,000 volts, 10 times higher. And heat, this is the silent killer of every modern chip. Your phone gets warm, your laptop needs a fan, data centers burn enough electricity on cooling alone to power entire cities. Diamond conducts heat 5 times better than copper, meaning it doesn't just survive heat, it moves it away before it becomes a problem. But here's where it gets interesting. Diamond is also radiation hard. In space, silicon chips get bombarded by particles that corrupt data, damage circuits, and shorten the lifespan of satellites and rovers. Diamond barely flinches. NASA is already funding diamond detector research specifically because of this. More power, less heat, radiation resistant, and it's made from carbon, the most abundant element in the universe.
Now, before you go thinking diamond chips are 6 months away from being in your iPhone, we need to talk about the hard part. Let's start with size. The silicon wafers used in modern chip manufacturing are 12 inches across. The largest diamond wafers in production today, 2 inches. That's not a minor inconvenience. That's an entirely different industry that doesn't exist yet at scale. And unlike silicon, which has been refined in massive factories over 60 years, diamond wafer production is still in its infancy. The processes, the equipment, the supply chains, none of it exists at the level silicon has. Then there's price. And here's something important. The diamond itself isn't the expensive part. Diamond is carbon. Lab-grown carbon is cheap. What's expensive is everything around it. The equipment, the process, the yield. A standard silicon wafer costs somewhere between $500 and $1,500. A comparable diamond wafer between $12,000 and $13,000. 10 to 30 times more expensive. Right now, the only customers who can justify that number are space agencies, military contractors, and nuclear facilities, places where failure isn't an option and cost is secondary. But here's where it gets interesting. The biggest unsolved problem isn't size or price. It's something called doping. To make any semiconductor work, you need to control how electricity flows through it, and you do that by injecting specific atoms into the material. Think of it like this. Imagine a highway. Doping is what decides whether cars drive on the left side or the right side. You need both directions for traffic to work. With silicon, both directions work perfectly. With diamond, one direction, called P-type, works well. The other direction, N-type, is still a major unsolved problem. The atoms you'd need to use keep forming defects inside the diamond that cancel out the effect entirely. Without both directions working, you can't build the complex logic circuits that power modern computers. And that's why diamond right now is excellent at one thing, handling extreme power and heat, but can't yet replace the chip in your laptop. Commercialization? The most optimistic realistic estimate is the mid-2030s. Not next year, not 5 years from now, a decade. But every single one of these problems is an engineering problem, not a physics problem. Physics says diamond can work. Engineering just hasn't caught up yet. And historically, that gap closes faster than anyone expects.
Let's say the engineering catches up. Let's say by the mid-2030s, diamond semiconductors are real, scalable, and affordable. What actually changes? Start with AI. Right now, the biggest limitation on artificial intelligence isn't software, it's heat. Data centers running AI models consume as much electricity as some small countries, and a significant portion of that goes purely to cooling. Diamond chips running at higher temperatures with less heat loss don't just make AI faster, they make it possible to run at scales that silicon physically cannot support. Then there's the power grid. Every time electricity travels through a conventional switching device, some of it is lost as heat. Diamond switches operate at higher voltages, higher speeds, and with less loss. Multiply that across an entire national grid, and you're talking about recovering billions of watts that are currently just disappearing into the air. Electric vehicles. The power electronics inside an EV, the systems that control how energy flows between the battery and the motor, are currently limited by what silicon can handle. Diamond components could mean faster charging, longer range, and systems that last the lifetime of the car without degrading. Space. This is where diamond doesn't just improve things, it enables things that currently aren't possible. Radiation-hard chips that survive deep space missions without shielding mass. Power systems for spacecraft that operate further from the sun than any solar panel can reach. Sensors that can stare directly at the sun without being blinded. And that last point matters more than it might seem, because the next step in human space exploration doesn't just need better computers, it needs technology that can survive environments that would destroy everything we currently send up there. Diamond semiconductors won't be in your phone next year, maybe not even in 5 years. But the trajectory is clear. Every major government, every serious research institution, and the most advanced military technology agency on the planet is betting on this material. Silicon had its era, and it was remarkable, but physics doesn't negotiate. The question was never if diamond would replace it. The question was always when. And when it does, space travel changes completely. Diamond chips can survive radiation that destroys silicon. They can operate in temperature extremes that no conventional semiconductor can handle. For any serious long-term mission, to the moon, to Mars, beyond, this isn't optional technology. It's a requirement. But here's the uncomfortable truth. Electronics are not the only thing radiation destroys. It destroys us, too. Diamond chips can protect your computers on a spacecraft. They cannot protect the humans inside it. And for that, you need something else entirely. Something that doesn't exist yet, but might. A technology so ambitious that the people working on it are the same ones who built the most powerful particle accelerator in human history. An artificial magnetic field.
that's a conversation for another time.